Hello everyone, I'm Zhu Bing from the Chinese University of Hong Kong. Our paper topic is hotspot detection via multitask learning and transformer encoder. Hotspot is a critical issue in chip manufacturing. Although some techniques can help avoid the hotspot generation, some low fidelity patterns are still hotspots. Lithography simulation is an effective method but extremely time consuming. To improve the efficiency, more methods are proposed. Pattern matching overcomes a time-consuming drawback but fails to detect unknown hotspots. Different from pattern matching, the machine learning-based methods learn from existing data, which can also detect unknown hotspots. They prove to should have strong generalization abilities and achieve good performance. Our work follows the machine learning directions. Briefly speaking, there are two perspectives. Most frameworks detect whether the center of an input clip has a hotspot, therefore it can be treated as a classification problem. Another perspective is detection perspective. The model can detect large layout clips with multiple defects. Although previous work has achieved great success, there are still some issues. The first problem is that method from classification problem is time-consuming since the layout pattern has to be divided into a lot of clips. One work proposed in Deck 19 solves the problem from detection perspective, but the whole framework is a two-stage detector. We hope to design a one-stage detector with higher efficiency. The second motivation is that some underlying information has not been utilized in previous work, like the corner information. Actually, they are also helpful proved by some work in computer vision area. Therefore, we also hope to incorporate them into our model. The third motivation is that we observe a situation where two regions with the same layout patterns have different simulation results. This phenomenon indicates that we cannot judge whether a hotspot exists only by focusing on the local layout patterns. However, convolutional neural networks commonly adopted by previous methods are infeasible to capture the long-range dependencies due to the locality inductive bias. To solve these issues, we propose our own methods. The whole framework can be divided into three parts. The first part is a backbone, acting as feature extractor, and the localization and classification head are used to report detection results. As for the corner and center head, they are auxiliary branch in our framework. I will introduce them in details. The backbone is composed of ResNet 15 and feature pyramid network. Different from previous work, we do not concentrate on the design of the convolutional neural network for feature extraction. Instead, we directly adopt ResNet 15, a very powerful feature extractor. Besides to jointly utilize the feature map from different layers, we build the feature pyramid network on top of the ResNet. As shown here, we generate multi-scale feature maps, and all of them can be used for detection. We found that the detection result on multi-level feature maps is more accurate and robust. The next part is the localization and classification head. To report the detection results, we define M anchors for each pixel of the feature map. Take the classification head as an example. The feature map is first fed into the conv layers module, and then an aggregation module is adopted to enhance the representation ability. This module will be introduced with more details later. The augmented feature map will be fed into the last layer and output a probability map where each element predicts the probability of each anchor containing a hotspot. For the regression head, the last layer predicts the offset from each anchor to a nearby ground truth hotspot. Then let's tap into the next part, the center and corner head. We design them to recognize center and corner information from the layout pattern. Their structure are very similar. Take the center head as an example. There are two branches. One branch predicts the probability of each point in the layout and being a center, and the other branch predicts the offset from each point to a nearby center. The heat map represents the probability distribution of center. The last one is the feature aggregation module. Before introducing more details, let me give the preliminary on multi-head attention and transformer, which is the basis for this module. Recently, transformer has made much progress in sequence-to-sequence tasks. Transformer is built on a core mechanism called multi-head attention. The architecture and the corresponding formula are shown here. Roughly speaking, transformer can build the relationship between any two features in a sequence or feature map. That's an important reason for the global attention ability of transformer. We hope to solve the locality inductor bias by globally capturing the dependency between different features in the feature map. Inspired by the transformer encoder, we designed a feature aggregation module, but if we simply adopt multi-head attention by augmenting each feature map with all other features, the computation cost is expensive since the key set includes hundreds of candidates and the complexity is HWC squared. In terms of this issue, we designed a simple but effective algorithm to reduce the amount of the selected keys. The main idea is to leverage the knowledge from the center head and corner head to guide the key selection, which help decrease the size of key set. Based on the new generated key set, the complexity reduced to KC squared, where K is much smaller than HW. Lambda is a hyperparameter to control the augmentation degree. Okay, these are the results for our model on the Iccad 16 dataset. The results illustrate that our model performs better on each case. The average accuracy of our framework achieves higher than previous work. Besides, our model also achieves higher efficiency and less false alarm. To investigate the behavior of our designed components, we carry out evaluation studies to confirm how different configurations affect performance. For example, with the center head and corner head, we get around 2% improvement on accuracy and a reduction on average false alarm. In conclusion, we propose a one-stage detection framework. We utilize the corner and center representation to improve both classification and location accuracy. Our feature aggregation module aggregates different features and augments the representation ability. We also design a sampling strategy to reduce the computation cost effectively. Okay, that's all for my representation. Thank you.